Can you hear me now? I hope everything is working with the sound now. Okay, we're gonna do Graded Lab 3 today. I'm gonna get you started on it. The rest is then to be completed yourself autodidactically. And let me know if the sound is working or not working. That would be great. Thank you. We're gonna do comparisons of two samples today. Hypothesis testing for two sample means. We're comparing two means. We do paired and dependent samples, which is important because you compare two situations before and after. And that's, as you can imagine, something that you will see quite frequently. Graded Lab is obviously not due in March. It's due on 11/8, 9, 10, 11/10. And yeah, so this will contain essentially the creation of a table 1 Graded Lab. So when you write a scientific paper that you may all do at one point, or you may report some study results in some form or function, you will always need to create a table 1. Table 1, the quote unquote table 1 is the demographics table where you have all the information in there. If you pursue a research question, you will contain in table 1 also a stratified analysis where you have your participants with one condition versus another condition. In principle and in broad strokes, you always have in all analysis, you have an exposure and an outcome. Your exposure, for example, could be anything. It could be kidney disease and the outcome on blood pressure, for example. Classical example that we have done now repeatedly. If you have chronic kidney disease, you would stratify as per Ckd stage 3 or worse, versus no Ckd on stage 1 and 2. So your exposure here is essentially earlier stages of Ckd and then later stages, and you essentially would stratify such. Your table 1, and we will look at this, will essentially contain then all subjects in one column, will contain your early Ckd stages and your later Ckd stages. But we will look at this later in Graded Lab. Any questions concerning the curriculum, concerning any of the earlier graded labs, or any other topics? Final project, how's that going? Had any ideas with some good topics? If you have any ideas, shoot me emails. I find your literature, I send you a literature back. Just look at the list of parameters and variables that are in the enhanced data set. You're welcome to also scout through the CDC website, find your own data. You can go on the CDC website, find enhanced data that essentially is not contained in that sample data set that I've sent you. It's like, it's fair game, it's open game. It's like whatever you're interested in. You can even go as far. You can go on the NIH website. The NIH data repository allows you to download ample data sets from randomized controlled trials. Everything the NIH has funded is public domain. Means this is easily and openly accessible to everybody in a de-identified fashion. So you can download this data, you can work on that. It's like, I'm game for anything. And actually, usually I want to learn from you as well what you're going to find and what ideas you have. So it's bi-directional kind of synergistic process. Yeah, first analysis plan is due. We do a quiz next week, which is going to be a more practical quiz. So you will do some calculations, some simple calculations. Not too complicated, but it's gonna get you in a feet a bit. Not too terrible, but it's gonna be fun. Then we do practice lab 7 and 11/18, and this is when the first draft is due. And I need to enforce this, unfortunately, because otherwise it's too tight. We only have. I need to grade. I am being asked to grade this the latest by 12/17. So this is in 6 weeks. Not even.
When is the first draft due?
Yeah, what?
When is the first draft due?
11/18. So in 2 weeks from now. So that will include that will basically include an analysis plan and a first draft and outline. So I would like to see in there already a broad idea of what methods you want to use, and also kind of the bullet points you want to discuss and address and analyze. So it should be quite advanced in thinking already. So the next 2 weeks really dig in, and that gives us more time to also refine it, right? Should be a good product. It could also be that could also be the basis for whatever project you want to do later on. If you want to really write this up, or you really want to advance with that, you're welcome to use whatever you're producing in this. I'd be happy to help you after this class as well, if you really want to do something with this data. So everything is fair game. But enhance, you also got to keep in mind there's some more complex methods, and I want to make this point right now. The analysis we're doing with the enhanced data, this is not generalizable data. So you need to approach this analytically a little bit more complex with a certain complex survey design that actually is not as easy as we're doing it here in class. But this can all be overcome. So if there's interest, we can do anything that you want to do.
Recording in progress.
Okay. Are you double recording it? Okay. Okay. Let's hide this. Well, turn me off, otherwise I hear myself. Okay, let's get started with the lecture that we get to the coding. Okay, we're doing hypothesis testing for 2 sample means today. This is module 9, so we have only a few more. We're going to do mainly parametric testing now for a little further. Then we do one non-parametric test, which is the chi-squared test, which is the comparison of proportion and counts. And then we quickly go in the realm of predictive analytics and regression. We're going to talk about a univariate regression, multiple regression, and logistic regression. Logistic regression particularly interesting because you will be essentially be able to analyze outcomes. So binary outcomes, which can go as far as hospitalization, yes, no, death, yes, no. Data that you don't have at your disposition, but we can actually, so that is a data set I actually would have. If you're interested to do mortality data on the enhance, I should have a data set available for you. Good, we're gonna learn today to identify when to use independent and paired two sample t-tests and set tests. We identify the underlying assumptions of these 2 tests, we perform these tests, and we construct confidence intervals, paired and unpaired, which you have done already. So it's nothing new, essentially. It's just as a review. So we have a 1 sample confidence interval and hypothesis tests using the set test. It's basically you have underlying a normally distributed population. But let me make that smaller too. You have a normally distributed population with a known sigma and a very large n, or a clearly normally distributed data. You can construct the confidence interval, and this formula is really important. So confidence interval is always to be calculated with your mean plus minus the set, which is your critical value, which in most cases is 0.025 as an alpha half, and 5% on both sides, which translates into minus 1.96 and plus 1.96. And this is a formula, this is a set code that you really should recall. If you do data analytics, this will come back repeatedly. If you do this from a sample, it's essentially the same situation, but you use, instead of the set, you use the t, and the t comes from the t table, the t-square table that you have in your modules. You can download these from the modules, and this will differ from the set test, but everything exceeding 30, and this is like this magical threshold of 30. So whenever a statistician asks you what's the sample size you want to at least go to, 30 is always a good answer, because this is kind of the threshold upon which most statisticians give you a green light to use a set test rather than a t-test. So this confidence interval estimation, as soon as you're over 30, you usually can use the set of 1.96. Everything below, you actually asked to use the t-score table. So the t is calculated as we have done with x bar minus mu 0 divided through the standard error of the mean, calculated as the sample standard deviation, which differs from the population standard deviation by the subtraction of n minus 1. If you remember, you use the degrees of freedom now, which is n minus 1, the sample size minus 1. Standard error is then calculated by the standard deviation divided by the square root of the n. So what's important to understand is now the main concept. So we have two kinds of observations. If you have, and we talked about table 1, if you have two populations, or you have one population and you have two samples from this, you have the exposure of chronic kidney disease, earlier stages, advanced stages. You get two sample populations, and you want to compare these two sample populations. Each individual in these two groups is independent of each other, right? That's two different samples. If you have a paired setting, you have one individual measured at some time point, and then the same individual measured again. So it's a repeated observation. And this analytically, it gives you a stronger feel of what's really happening. So it's analytically a little bit simpler and a little bit more robust. But essentially, you get a dependent measure and you compare it differently by calculating the difference and doing the hypothesis testing on the difference. And we will look at this now. So examples of unpaired measurements are birth weights of boys and girls, laboratory results from different participants in the clinical trial, household healthcare costs in US versus Canada. There are ample opportunities of different examples, obviously. Right? If you have paired measurements, you have birth weights of twins, you have pre and post lab results, ocular measurements on the right and left eye, stress measure scores in twins, so husband-wife pairs, measurements of two methods conducting assay. This is a tricky one. So you would still treat this as paired measurements, although it's the same individual, but you're still treating them in the same way and fashion. There's actually a very strict analytical procedure how to compare two methods being used on the same individual, because this difference between two methods is called a measurement bias. And this bias, essentially, you can then nicely analyze. It goes too deep now a little bit, but usually you have the difference. You get for each individual a difference, and you want to see this then as a scatter plot shown as the magnitude of the measurement to see whether there's an error with a, so you want to measure creatinine or you want to measure blood pressure, and you have two different methods, and you get a difference for each individual between the two methods, and you want to see whether this error gets larger with larger blood pressure. So you would analyze this as the difference as a function of this measured blood pressure to see whether the error gets bigger or smaller with an increase in blood pressure. Because many methods get more inaccurate. They have more error when the measurement magnitude is actually larger. That's the reason why. It's called a proportional error. So when to use a paired t-test? So you compare heights of males and females before and after. You compare anxiety levels before and after. You compare an anxiety level of two groups. So that as a question, which one would strike you as being the one that you essentially want to use in a paired setting? When you would read this as a question on a quiz, which one would you choose? Yes, it's two. Before, one thing that always will prompt you for a paired setting is where you have a chronological order. So before and after screams paired setting. So that keep in mind, because that's something that could come on the quiz. Blink. So keep that in mind. Okay. The relationship between the one sample set test and the paired sample t-test is now that in a one sample, you have an x bar minus your mu divided by the standard error of the mean. The difference that you have now for a paired setting, you have a before and after condition. You calculate the difference. And if you compare this difference against 0, you essentially hypothesis test whether this difference significantly differed from 0. If it's 0, then there was no difference, right? So this is essentially what you're implying. So you're implying a one sample set test or t-test against 0 with a difference, notably. So it's a mean difference for each of your participants. You calculate it for the entire sample population. You take this difference and you compare it against 0. That's your hypothesis test. Same here with the t. You're doing the same thing. You're employing the t, and the threshold is again 30. Over 30, go for the set test. It's clear, right? It's logically, but it's very nice to see it mapped out and see it in front of you as a formula, because it makes it very obvious what actually is done. So examples are, for example, and this is the example we're going to be looking at. So that's the cell phone use while driving impair reaction times. Classic example, and I don't know whether you know that Discovery Channel show Mythbuster, where they tried like cell phone use before and after, and alcohol intake before and after. So they did all kinds of experiments, and they actually in vivo tried to test reaction times. It's actually a pretty cool show. So I liked it back in the days when it was still on. So the question is, does cell phone use impair reaction times? So you had students that would simulate a driving situation, and at irregular periods, you get a target flashed up, either red or green, and you need to react to that. When this flashes up, you're supposed to press a brake button. So the experiment analyzed mean response. 32 students were randomly assigned to the cell phone group, 32 to the control group. What kind of test would that be? This is unpaired, exactly. So now we have cell phone use and no cell phone use. So we have cell phone use, cell phone group, and control group. What do we see? We see here, this is a box plot. Who remembers what a box plot shows? Okay, so what is the bar here? This guy. It's the median. It's the median. So the median takes every entry and takes the middle entry of the entire group. Well, can we actually see? Oh, you see that mouse too. Okay, great. That's actually nice. Okay, so we have the median here. What is the median? The median is Q2, right? Q2 is the middle of the whole group. What is this here? The lower end of the. That's Q1, correct. That's 25th percentile. Then we have this. What is this? Exactly. And Q3 minus Q1 is what measure of variability? Interquartile range, correct. And now the million-dollar question, what is this? What is the end of the whisker? Now the outlier would be that guy over there. That's the outlier. But what's the end of the whisker? That's my question. No. No. It's a misconception. It's a common misconception. It's not. It's a standardized distance. And it's a tricky one, because you will find out in the field, you will find, and I'm flagging this, a lot of people will not know what the whiskers mean. You're close. So it's Q3 plus 1.5 multiplied by IQR. So it has a Markov variability which is related to Q1 to Q3 to the box, but it's 1.5 times the IQR. But I'm flagging this because a lot of people don't know that. It's actually it's a fun fact to know, and I'm full of these fun facts. So I like those. Okay, so this is here. Can you see from this? So there's a difference, right? There's a difference of almost like 50 milliseconds. So it's quite something, right? Can you see from this graph whether this is significantly different or not? Just yes or no. Can you see it?
Not significant. You can see it's different. I don't know if you can say it's.
You cannot. Likely it will be, but you cannot say it because you don't have this measure of variability, right? You would need to calculate the set score. You would need to see the confidence interval. This is also not necessarily normally distributed. Well, it kind of is, but essentially you need to analyze this first. So in this population, we have treatment and control. Population is mu C and mu T. So if we focus on the hypothesis testing of the null hypothesis, in this case, mu C would be equal to mu T. That means that mu C minus mu T should be 0. So now we're analyzing the difference in means, not the difference in individuals. So it's the difference in means, it's not the difference between individual scores. So it's not the mean difference, it's the difference in means. And this is where wording makes a huge difference. And this is, it's tricky at times. So the quiz is not going to be that complicated, but essentially it's, keep it in mind. So the way you would analyze this is this formula. You don't need to know the formula, but you need to kind of understand what it entails. So you're treating this as if you would have drawn repeated random samples, and you get a sample 1, sample 2 mean. That's the x bar 2 minus x bar 1 minus the mu 2 minus mu 1. So this is essentially what you would then divide by the standard error of the mean, which here you need to aliquot to each sample population, because in an independent sample t-test, these could also be different n's. So you need to aliquot it, and this is called a pooled standard deviation. Here it is without pooling, but this arithmetics are not necessarily too central now. If you pool it, you simplify it, and you can calculate either your set or your t. So pooling or not pooling, it's safer to not pool, but if you not pool, you need to pay attention to what extent your standard error, deviation 1 and standard deviation 2 differ. If they differ more than a factor of 2, you are meant to not pool. As another rule of thumb to override the previous, do pool if n1 or n2 is less than 5. Why is that? Because the smaller your sample size, the more your deviation will be found. The larger your sample size, the more normal, quote unquote, normal it becomes, and the narrower the distribution of the mean becomes. So pooled standard deviation can be pooled in that way. So we talked about the unpooled, we talked about the pooled. This requires you to estimate the degrees of freedom. This is not necessarily something that you need to know, but you essentially are treating it individually. If you do pool it, you need to subtract both groups. Groups will always be n-1. 2 groups is n-2. If you have an unpooled standard deviation, you subtract 1 for each estimate. But in essence, you will have software do that for you. The only thing you need to really distinguish is whether you have equal variance or unequal variance. And this you can, so by default, R, for example, would do equal variance by default. No, unequal variance by default, and would assume this to be unequal and would treat them in a pooled setting. If you know the variance is equal, you can define it as being equal. Yes.
When you say that unequal variance, does that mean, like, let's say, in our example that we had, like, how different both samples are from the whole population? And that's unequal.
It is the standard deviation, right?
What variance are we referring to?
We're referring to the sample variance. So the question was, what does equal or unequal variance mean? So this means the standard deviation was in the sample. So the standard deviation, to what extent the variance between the samples differ. So this is what you would define with unequal or equal variance. If you go with unequal variance, you're probably on the safer side. It's the so-called Wilks test. Yeah. Okay, so you choose an alpha. Let's choose it here for 0.05. You assume a null hypothesis for mu control minus mu t cell phone. No, mu cell phone minus mu t is 0. You calculate the test statistics, and you essentially come to a t of 2.628, which corresponds with a p-value of 0.011. So the t exceeds your threshold, so your null hypothesis is rejected. So this essentially is a significantly different result. But you can't judge it just from looking at medians. Okay, the conclusion is, and this is important for the interpretation of the final project, the conclusion is that the mean response time of cell phone users is significantly different, greater, than the control group. Greater, you should not include any alternative hypothesis because then it becomes a one-sided setting. So you should always say it's different. And you can then, in a second part of your conclusion, you can state that it's greater. Okay, so now let's continue. So the cell phone analysis presented earlier used independent samples. So one group used cell phones, the control group did not. So now we can design it differently. We can pool all 60 participants in the same pool, and we can make them test the reaction times first with a cell phone and then without a cell phone. What's the problem with this design? Just to think about it. What could be one of the problems in terms of research design? Think about it. You do something the first time, you don't know how this is going to go. You do it the second time, you're learning, right? So this is where you can do think of a crossover design. So you can actually then split your entire population. You have them both do the same exercise, but you split them in a way and you randomly assign them who's going to start first with using the cell phone and who starts without using the cell phone. By that, you factor out this confounding effect of learning. Another in medication settings, for example, you would do with crossover designs, you would do between a before and after situation, you would have something that is called a washout period. So you do before using the medication or using another medication, you essentially have between those two phases a washout period during which the medication is entirely eliminated, loses its effect, and then you get the individual on the other intervention, which is not possible here with the cell phone because they would need to forget how to do that, but it's not happening. So that would be essentially how you approach this, how you can approach it. And here's the actual data. So here you have the difference shown using cell phone and using cell phone. No, yes, no, yes, no, yes. You have your 32 individuals. You have here some that actually got worse. You have some that got better without the cell phone. And these are now pair differences. So for each matched pairs, you calculate the difference. You have this difference D. And this reaction time minus the reaction time without the cell phone. Your hypothesis testing against a hypothesis difference, a null hypothesis difference of 0. So now you can use a set or a T method, and you choose the test to assess your assumptions. The variables are quantitative and different score for each individual. You choose a pair sample t-test for the means. The difference scores are approximately normal. And the data is observed and obtained during a random process. So again, you choose your alpha, just like the random, the normal, the usual hypothesis testing. You choose your alpha, which is 5%. You write a null and an alternative hypothesis where the difference equals 0. And the alternative hypothesis in a two-sided test again would be that it's unequal to 0. Calculating this was a t-test, although you could hypothetically with this sample size also do a set test. You're calculating the difference of 50.6 divided by the standard deviation of 52.5 divided by the square root of the sample size, which is 32 individuals, because you tested 32 individuals before and after. So you basically, your sample size is now the sample size of the differences, not the sample size of both groups anymore. So the T of 5.46, we see that from the T-score here is greater than the alpha critically, which essentially we have here a confidence level of 95. We go to 30, which would be 2.04. So 5.46 is greater, degrees of freedom 31. And you have essentially a significantly higher difference than 0. The box plot shows a skew to the right for the different scores. So two-sided inference is robust to violations of the assumption of normality, and you don't see any outliers. So you are solid and robust in your assumptions, in your conclusion. CI for difference of means. So check whether the 0 falls into the CI. Again, the same principle as we have learned for the set test. If the 95% confidence interval does not overlap the 0, you have a significant difference, significantly different difference from 0. So your null hypothesis is to be rejected. So if all values of the CI are greater than 0, so the upper bound and the lower bound are greater than 0, you can infer that mu1 is greater than mu2. If it's smaller, it's shifted to the left, means your mu1 is smaller than the mu2. Important to keep in mind that you are constructing this confidence interval now for the difference, and it's not for each sample. So that's a different approach. So here you see it graphically depicted. You basically see here this difference plotted, and this does not necessarily constitute a significantly different result. So if the confidence intervals overlap of the sample, you don't know for certain that your difference, that your two results are different. So you need to test the differences. So two sample procedures. When you have paired samples and you have continuous parameters, you have continuous variables, you calculate the differences between paired observations, or you compare the difference between means in independent samples. You use T or set distribution with slight modifications, and you use a one sample T or set methods, just as you use the set statistic comparing a sample versus the population. With proportions, you can take differences between proportions in independent samples, and you can use sample set methods. And we have covered these methods where you use the normal approximation to actually compare proportions against each other. The paired samples proportion comparison, that's a McNamara test, is not covered in this test, in this course. Is that clear so far? It's logical, right? It's pretty much in line. It's a continuation of our thinking on hypothesis testing. So what is important to keep in mind that the samples really need to be independent for an unpaired t-test. There should not be any connecting factors between them. For paired, the pairs are a unit, which is the same individual in most cases when repeated measurements. Population values are normally distributed and they're obtained by random samples. Random sampling is also important because otherwise you get biases in your observations. What are limitations? We have discussed some of these limitations already. So statistical significance is not necessarily practical significance, which means particularly when you have very large data sets, which is a problem that we have observed already. We haven't discussed it, or I may have mentioned it. So if we have our large enhanced data sets, this is most likely resulting in a significant difference, which is easy for purposes of teaching and makes things a little bit easier to show. But you need to keep in mind that when you have a significantly different result from a large sample size, that doesn't necessarily mean that it's really a relevant result. And that's a problem, right? If you have a blood pressure lowering drug that lowers the blood pressure by 0.5 milligram Hg over in 5,000 people, that may not be clinically relevant. Then you really need to understand the distribution of your result and your effect. So this is important to keep in mind, particularly when thinking about differences of that kind. You really need to look at the variability, and you really need to test whether your variability actually justifies the intervention that you're studying. So this is important to keep in mind. Confidence intervals are in that regard very, very informative and help you to understand the distribution of your sample. Here's the example of a minimum bid on eBay camera on a sales price with 341,000 bids. So, and you see essentially that only a confidence interval essentially is here inside for, and the increase is essentially not necessarily that informative. So large samples can be problematic. Secondly, the second most common misinterpretation is that no evidence of a difference essentially implies that there's evidence of no difference. That does also not necessarily mean. So you essentially, the evidence for a null hypothesis is called a power. That means that when you do not see a difference, is there really no difference? Otherwise, you're gonna run in what error? When you do not reject what you should have rejected? Type 2 error, yes. So type 1 error is where you reject something that should not be rejected. Type 2 error is where you do not reject what you should have rejected. Number one reason for type 2 error, which is a huge concern, is that you do not have an adequate sample size, which is a huge problem, particularly with trial design, where you conduct power calculations, which we will do, that essentially allow you to estimate the sample size needed. An example could be that researchers did not find any effect of treatment on self-reported pain level. So that's the example we had right in the beginning, if you remember. So does this mean that there's an 80% chance that the pain reliever has no effect? When they don't know, it's a 20% chance. It's 1 minus the 80. Second common misinterpretation. Although alpha of 5% is a common cutoff for the p-value, it's not carved in stone. It's not the golden rule. It's something that is established over the years. And so there's actually a paper I can try to find this paper. There's a paper when this actually happened that the scientific community embraced 5%. It was actually from the statistician, a famous statistician that Fisher's exact test is also determined by him. So Fisher was a famous statistician in the 20th century. And he actually had a publication in the 1950s or 60s where he mentioned this 5% cutoff value. And since then, this has just found its way into the scientific community. But that doesn't mean that this is like always to be embraced. So if you see variability, if you see effects that are still in your mind worthwhile reporting, I wouldn't see a problem also reporting a p-value of 10%. If it's relevant, if it makes sense, if it's a dramatic difference that you see, you may still do something good for the community to report it. It may still be hypothesis generating. It still may be something important to interpret and to keep in mind, and maybe down the line for future studies to just consider as an alternative outcome or as an additional outcome. You never know. So I think even negative results should always be reported. So whatever insights you have is worthwhile reporting, in my head. So I started with two primary endpoints as an example. Gets a p-value of 0.055 for one endpoint and 0.04 for the other endpoint. Should this be interpreted as strong evidence for one endpoint and no evidence for the other endpoint? Again, there's a difference of 1.5%, right? Just because it crosses this threshold doesn't mean it's useless insights. It still may be very, very valuable to understand what caused this difference. It's also when you keep the p-value, the calculation of the p-value in mind, it's a probability. It's nothing else but a probability that is dependent on the sample size, it's dependent on the variability within your population, can be dependent on various factors that you have not taken into account analytically. Misinterpretation number 4. Significance tests are not about individuals in a population, they're about populations per se. What trained us now in a randomized controlled trial, and here's the example of children with lab contamination. If you sample children that had a lab contamination, which is a serious kind of incident, right? If you have insights about individuals having such an adverse event occurring, it's still worthwhile to understand what is going on. So if you see a difference in some parts of your population and in others not, there is really where you should dig deeper and you should try to understand what happens in your population. If you have randomized controlled trials, for example, this is also where you do, you have an intention to treat analysis, where basically you look whether the intervention was effective, and then you have an as treated analysis, where you basically look into those that really took the blood pressure medication. And then also you can further substratify who had an effect, who had actually a significant effect in your population. So you go lower, you see whether it had an effect in women, whether it had an effect in diabetics, in those with cardiac disease. So you try to drill deeper and understand in your population who had an effect. And this again can be hypothesis generated. Maybe for your RCT underpowered and not as insightful, but could be important down the road for future research. So also to be kept in mind. So if you have a p-value smaller than 1%, okay, so this is, yeah, I hope this is clear that if you have a p-value smaller than 1%, this does not mean that fewer than 1% of children have a serum levels exceeding the limit. So it's a probability value. There's nothing to do with an actual score occurring or an actual result occurring. It's not a proportion, it's probability. Assuming that because n is small, you cannot believe any results of a significant test, or conversely, because n is large, the results must be true. Also not true, because you need to understand again the distribution. You always need to see how does the distribution of the population look like, and how could some in the population still benefit from the intervention, or some could not. And that's the most important thing, which I mentioned right from the beginning. It always comes down to descriptive statistics. You need to understand your data, you need to map your data out, you need to graphically depict it, and you need to understand what you're looking at and how you're analyzing what you're analyzing. Good. Oh yeah, almost forgot about that one. Okay, appropriate skepticism in interpreting significance test. Study design is critical. It is really dependent how you analyze data, how you interpret data, which includes flaws in producing the data. You could, for example, you have voluntary response samples. You talked about selection bias and sampling, right? If you have a convenience sample where somebody wanted to participate or somebody was chosen to participate because of any random fact that resulted in a convenience to sample this individual, you possibly looking at the selection bias of the insights and of the results. You can have uncontrolled experiments, and you can have measurement biases. You can have investigator biases where basically investigator were trying to shape results in a certain way. And it's just important that you really keep this in mind. And this is actually an interesting example in this regard. Then we have tests can be statistically significant by chance. Obviously, they can be non-significant by variability and by chance, but they also can be significant just by random chance. So green jelly beans are certainly not linked to acne. So from that end, you need to keep in mind whether replication will result in the same result. That also underlines that you need to understand what you're actually analyzing, what your underlying pathophysiological pathway could be, and you need to understand what the underlying hypothesis actually is. True effects may not be as large as initial estimates due to publication bias. That could be that, for example, things have been to some extent, they wanted to publish it. And for that reason, they did, how should I say, they analyzed very hard to find the effects they actually wanted to see. And so there's the article about the publication bias by Pfizer. What's important in this regard, and I have talked about this, I believe already, you will find every study, and we're already at the end here. I just quickly want to show you this. So every study that is being conducted will find its way into clinical trials. Clinicaltrials.gov is where every randomized controlled trial that is being conducted and is of significance. Is that a little better? So you can essentially, all studies, you look for chronic kidney disease. You can look up all chronic kidney disease studies that are currently being conducted in New York. As if there were that many New Yorks, right? Okay. So these are the Ckd studies that are currently conducted here in the US. So this is from NYU. This is patiromer, a potassium binder, recombinant human growth protein, vitamin D3 at Rockefeller. So you can go through all studies that are currently conducted. Columbia, Weill Cornell, NYU, Rogerson. And here, for example, that's us. That's actually one of ours. That's a left span. Then we have same here. That's also one of ours. Always got me. So RRI, that is, for example, a study we're currently conducting right now. So it emphasizes that you need to announce your study to the community. You need to say, okay, so this is our target, this is the power calculation, this is what we're doing. And by that, you increase the level of transparency. And by that, once you want to publish it, there's a clear trail of, okay, so I designed the study, I went on IRB, I declared it on clinicaltrials.gov, and essentially this is what I wanted to do, this is what I'm doing. And once the publication comes out, you quote your clinicaltrials.gov number, and your reviews will go back to your clinicaltrials.gov entry, and we'll see whether you're really reporting what you have done. So if you report, if you review reports or papers, make sure that you understand what the investigators did, what they announced they would do, and to what extent this differs from what they're reporting now. So this is important when you're reviewing papers. Keep this in mind. Good. All right. Any questions? It was a lot, I know. But it's an interesting topic. As you can see, it's relevant. This is if you're reviewing papers, if you're looking at grant applications, I don't know in what capacity you will be finding yourself again at one point in time. These things will be your daily bread. So keep that in mind. Any questions? If not, then we can get started on Graded Lab 3. And yep.
You take examples from papers and your snippets, or maybe you have to do that.
Enhance is not, so there are some resources on the final project module. So you can go through those. You can also just simply Google Enhance, what studies came out. You can, for example, also go on PubMed. You know PubMed, right? The National Library. So if you go on PubMed, you can just enter Enhance, and you will find all entries for Enhance. There will be millions of hypotheses, and I'm not forcing you to come up with your own ideas, right? It's like the enhanced data is one of the most well-studied data set on planet Earth, I guess. So you will definitely, you will have a hard time finding a hypothesis that hasn't been published yet in some form, shape, or form. You will need probably some time to go through all these approaches. One interests you, dig deeper whether you have the variables that you need. If not, go on the CDC website, download it. You have a sequence number, the SEQ number. With this SEQ number, you can essentially match your data that you get from the CDC with the data you have at hand. So you can do whatever you want to analyze. You don't have longitudinal data. So you only have cross-sectional data. Keep that in mind. I have hoped at one point to find longitudinal data, but it's also analytically quite complicated. So I think the cross-sectional data is a good way to go, because you can do all the things we're doing. You can do with the enhanced. You can even do logistic regression on the enhanced data without a problem. If you have a binary outcome, you may be interested in doing something. Or we get mortality data, but then again, you have, yeah, it's a little bit more tricky, but we can also do some mortality analysis if that is wanted. But here you see plenty of various hypotheses basically that were already done. And so you have ample ideas published. So I think this is probably the best way to go. Just go through PubMed, what you're interested in, any topic that is of personal interest, or maybe, I don't know, from a circle of friends, or I don't know. Be creative. And that creativity is actually part of research. because science is a lot about creativity and interest, curiosity. Okay, so then let's have a look at Creative Lab 3. So this is okay. So we have let's look into so if we go on Creative Lab 3, just find R. Okay, so the data file you have downloaded, you download it on your folder. You can now just input it quickly. I intentionally always have like CSV files to spare you any conversions or whatsoever. So if you df with .csv, quickly load this in. Okay, what is the idea of Creative Lab 3? So as said, it's there's a good chance you're not going to like me at the end of this exercise because it's quite intense. So this is a little bit of work. Okay, so you have the assignments to create this table. How are you going to create this table? You preferably want this table in a way and shape and a format that you can just copy paste it into a Word document, right? That's the preferred setting. One way to do that is you create, and this is my approach. So there are different approaches. I do it in a very simple way. So we are creating a data frame, demographics, which is going to be data.frame. And now data.frame, in data.frame, you're entering all the columns you want to have. So you have population, you have the overall population with Ckd stage before 3, the Ckd stage 3 or higher. You have males, females, women, and males and females, earlier stages or advanced stages. So you will need, first of all, you will need a header row, which is here indicated by saying, let's do this. Let's do variable. And then you do C by indicating there's more coming now. So we do Ckd stage. No, we don't need Ckd stage. Let's do sample size. Then we do comma H, comma SPP, comma TPP, comma EGFR. So if you do this, what will you see? So if you start demographics, you get this outline. You get variable, sample size, age, SPP, DPP, EGFR. And now, by going after this, you can extend this in terms of columns. So you go further to the right by creating all. So this is male and females, or you can do a CKD. Let's do no CKD or. And then let's do no CKD or mean. No CKD or SD, because it's going to be mean and SDs, right? If you put this in quotation marks, you have equals NA will populate this all the way, will populate this all the way down. So you create with data frame, you create now here variable. I don't make no space. That makes it a little bit more. Okay, so data frame variable gives you the column. Everything after the equal sign is going to be populating that column. The comma concludes that column. Everything after that comma will be the next column. So no CKD or mean is the next column. No CKD or SD is the third column. Gets you now up to a point where we have now this. And when you look at that, you already see where I'm going with this, right? Because you need here mean plus SD. So you do mean in this column, and you do mean SD in this column. And you can, with demographics, row, comma, column gets you row 3, comma 2. You can now populate, what was it there? Hello. And hello is a stupid example, but it emphasizes what we're doing, right? So you can address each of these cells in your column. And this is where you're going to get your mean in. This is how you're going to get your standard deviation in. And this is how you populate the entire table. Yeah, good. And this is a simple way. It's not a beautiful way. It's not aesthetically beautiful. And you can, so please amuse me and please impress me by doing it with for loops. You know what I'm saying, right? If you do it with for loops, you can run it through. You run iterative loops through the parameters, and you can. This is how I would do it in real life, right? It's like I do the same data frame. I do this in real life. It's like this is the way how I approach this, because by that I can export this data frame. Exactly this data frame. I can now export. So I can do write.csv. And I call this demographics. .csv. So I'm copying this now in the df demographics. I am creating a demographic CSV file that essentially looks exactly like this. I have here the mean, I have here the standard deviation. So now it's opened it stupidly with numbers, which I don't want to use, because you can do now in the last step, and I'm showing you this. so that you can do it at home then if you want to really get it in a format that you can just copy paste it in a Word document. So now if you convert this into an Excel spreadsheet, Excel as X, you can enter formula. So if this is now, let's say the SPB is 120, the standard deviation is 15. You can say, okay, I'm doing this, this, and you're just pulling this down. And you can say now your SPB is concatenate this quotation mark plus minus, because this is how you're reporting it in a publication, standard deviation. And this is how you get it in format that you can populate an entire row, an entire table in Excel. You have this concatenate formula that you just have to pull and drag, and you copy paste this as a whole thing in Word. When you need to make a change and you find an error, you have an updated spreadsheet, you just need to rerun your code, export it again, just copy paste your formula, run it again, and copy paste the whole thing in Word document. Takes you like 30 seconds, you're redoing your entire table. It's not easy, but it's worthwhile, because if you have that going, if you have that code going, you're good. You're good for whatever publication. So this is a trick from a real life setting. You can do it even easier. You can in R, you can do with the paste function. You can paste it in the cell, the plus minus and all of that. You can spare yourself even that step with the concatenate, but I'm not going to go there because this is going to be too confusing. Then the codes get long and the for loops are getting more complicated. It's a nightmare. So then that's for now, this is a good approach, but you see the value, right? Because it makes your life super easy. Down the road, it's like, this is how you want to do it. So what else are we going to do? So now we have demographics, write.csv, demographics. So sample size is easy, right? So now we have no Ckd, then we do Ckd or equals NA, then we do, oh no, yeah, then we do no Ckd or. But you see how this goes, right? Mean Ckd or ST. And so you continue until you have the whole row populated in exactly that format.
That's what a table 1 is.
This is your table 1. This is, you go in whatever publication. I can show you actually. Hold on. Let's go in whatever publication, event papers. By the way, if oh, it didn't. Oh, so if you okay, since we're talking about this already, if you're looking for a tool that allows for you to organize your publications, I highly recommend Papers. So this is from my own world. You basically are uploading PDFs. It will automatically map and recognize the PDFs, the names, and the.
It's like Mendeley, right?
It is in the same. It goes in the same direction. Yeah, I just like Papers more, because you actually, this is my cloud. This is my Papers cloud, and you can also have an app on a Mac, Windows. I have a work account. I have it on the iPad. I have it on the phone. I sit at a conference. I can check it on the phone. So it's gold. I find it better than Mendeley. but I've never worked much with Mendeley. It's good to organize your library. It's at this point not very advanced with the citing. So if you cite while you write, I prefer EndNote. I'm still working with EndNote. Which you likely have with the library, you have an account. You do, right? Yeah. So if you're writing your thesis or you're writing a paper or whatsoever, EndNote is the way to go. But you have for each study, you have the unique identifiers, and I don't know to what extent this was explained to you. I think Dr. Friedman does the lecture on You have the DOIs, you have the PubMed IDs. If you do PubMed IDs, you come from papers directly to the PubMed. So this all cross links. These unique identifiers you will also need then for essentially for your PubMed ID. Oh yeah, citations. Yes. But doesn't need to be much. So, but I will, if you give me the topic, I will send you a couple of papers that I find based on what you want to investigate, and you can find more or work with those that I sent you. But I will support you on that journey. So it's not something that you don't need to learn scientific writing overnight. So don't worry about that. This course is not about scientific writing. This course is about analytics in a scientific setting, not about the writing per se. So I will support you to the fullest. But yeah, so papers is good, definitely useful, and I would definitely consider it. Okay. What else? What else? Yeah, and if you go on any publication, you click into it and you will literally always find your table 1 somewhere. Sorry, it's okay, so this is not a good example. Here's table 1. This is your table 1. Then you have table 2, which is likely more specific already. Here for the analysis sessions. But it's always the same kind of, was a good one. Let's reviews. Here, classical table 1 from Gabi. Classical table 1. Here we go. And here you see already stratified and healthy subjects, HD patients. So this is along these ways you should think, right? And this is what I want you to do with Ckd stage 3, Ckd earlier stages, or stratified, non-stratified. All right, males and females, and a formal comparison. It goes a little further then. So this will keep you on your feet. But after graded lab 3, you're solid in R. If you tackle this, you're solid in R. You know how to run this. So, okay, so you also are asked to state the null and alternative hypothesis for a comparison of the proportions of Ckd stage 3 and non-Ckd between males and females. Proportions, comparison of proportions. Is binomial test or normal approximation. Difference between Ckd stage earlier and Ckd stage 3 in all men and women. Calculate the difference in means and calculate 95% confidence interval. You get that from a t-dot test. You remember the t-dot test formula? Yep. That's the columns that are to be added. Expressed as follows: mean difference, 95% CI, lower bound to upper bound. Only one decimal is enough. Here's the t-test XY. It's 3 more columns. Here's a contingency table. I also want to see the contingency table in anticipation of the chi-squared analysis that we're going to do in the following lectures. Here's the code. So I'm giving you that code, but you don't need to develop that code by yourself. So you can quantify this. You get a table. With table, you can do here the chi-square test. Final table should look like this. This is how the demographics table template should look like. So this is going to be annoying to do, but again, you're going to be settled after that one. All right, so this is all. Any questions? No?
I'm sure there will be, but I don't have any yet.
No, but please email me, and you're going to be fine, I'm sure. It's not difficult, it's redundant, it's a lot of work. So one student told me this was physically pain doing this table. But it's kind of, it gets you in the mindset, right? It's like it makes sense. Trust me, because it's easy to do, and you do something redundantly, and by doing it redundantly, you're learning it. It's unfortunately the way to go, and you will see. And really impress me. Do some loops. If you can do loops, go for it. It should be doable. All right. Thanks so much. Have a nice evening. See you next week on Thursday.
Sure. Yes.
All right. Bye-bye.